Let us start Unit 3, which is pure substance. So before defining the definition for pure substance, so let us discuss some basics about the pure substance. We know that matter can be divided into two types. Those are pure substance and mixtures. These pure substance may be element or it may be a compound. And same mixture may be homogeneous mixture and heterogeneous mixture. So from this graph what we can understand is any matter can be divided into pure substance and mixtures, and pure substance may be of element or it may be of compound, and mixture may be homogeneous mixture and it may be heterogeneous mixture. Example for pure substance are copper, teapot, baking soda, water. These are all example for pure substance. And similarly examples for mixture is tea and figs, so like that. And now we can define the definition for pure substance. A pure substance is a substance of constant chemical composition throughout its mass is called pure substance. So it is a one component system it is. So example may be water, it may be gold, or it may be NaCl. So you can observe for water and for gold and NaCl, chemical composition of these three material are same. That is the reason why we can call these as pure substance. So if you want to call substance as a pure substance, it should have chemical composition, which means that it should have a same chemical composition throughout its mass. Such substance we will call it as pure substance. So let us discuss about PV diagram for pure substance. So for that, assume a unit mass of ice, you can call it as solid water, at minus 10 degrees Celsius and 1 atmospheric pressure contained in a cylinder and piston machine. You can see that in this figure, okay. Let the ice be heated slowly. Let the state changes of water be plotted on PV coordinates. The distinct regimes of heating is as shown in the figure B. Okay, this is the figure B. In the figure A, we have assumed a unit mass of ice at minus 10 degrees Celsius and 1 atmospheric pressure contained in a cylinder piston machine, and let the ice be heated slowly. And in the figure B, the state changes of water be plotted on PV coordinates. The distinct regimes of heating is as shown in the figure B. And you can observe this PV diagram here. 1 to 2 you can see in the diagram here. From 1 to 2, the temperature of ice increases from minus 10 degrees Celsius to 0 degrees Celsius. The volume of ice would increase. You can observe here the volume of ice is increased from 1 to 2. Clear? At state 2, that is this point, ice would start melting at point 2. And similarly from 2 to 3, ice melts into water. Ice melts into water at a constant temperature 0 degrees Celsius. At state 3, here the melting process ends. So there is a decrease in volume. You can observe from 2 to 3 there is a decrease in the volume, which is a very peculiar property of water. Okay, you can observe from 2 to 3, if you keep on hitting from 2 to 3, after state 2 if we keep on hitting, actually the volume of water should increase, but instead it is decreasing. That is the peculiar property of water. Now from 3 to 4 again volume will start increase. The temperature of water increases upon heating from 3 to 4. From 0 degrees Celsius to 100 degrees Celsius. The volume of water increases from 3 to 4, you can observe, because of expansion. And from 4 to 5, the water starts boiling at state 4. Here it starts boiling at 100 degrees Celsius, state 4, and ends at state 5 at a constant temperature 100 degrees Celsius. And from 5 to 6, the vapor is heated say up to 250 degrees Celsius, which means that more than 100 degrees Celsius at state 6. In the diagram, we can observe that the states 2, 3, 4 and 5 are known as saturation states. A saturation state is a state from which a change of phase may occur without change of pressure or temperature. And state 2 is saturated solid state. You can see the diagram, earlier diagram. State 2 is saturated solid state. State 3 and 4 saturated liquid states, and state 5 saturated vapor state. If the same heating is done at a different pressure, say 2 atmospheric pressure, in earlier concept or in earlier slide, you can observe in the diagram that we conducted or we have heated ice cube under the 1 atmospheric pressure. Now, if the same heating is done at different pressures, say 2 atmospheric pressure and 3 atmospheric pressure, similar regime of heating would have been obtained. All the state changes of the system can similarly be plotted on the PV diagram or PV coordinate, which you can see in the earlier slide, when it is heated at different constant pressures. If we repeat the heating of ice cube at different constant pressure, and we will get this resume. How to get this resume? Let us see. The line passing through all the saturated solid state 2. We can observe here the line passing through all the saturated point 2 here is called it as saturated solid line. Similarly, the line passing through all the states 3 and 4 is called the saturated liquid line. The line passing through 3 and 4 call it as saturated liquid line. We can observe here saturated liquid lines. Similarly, the line passing through all the point 5 is called saturated vapor line. Here saturated vapor line. Then the triple point is a line you can observe. Okay, this line you will call it as triple point. The triple point is a line on the PV diagram where all the three phase solid state, liquid state and gaseous state exist in equilibrium. So such point or such line we will call it as triple point line. And now at a pressure below this triple point line, the substance cannot exist in the liquid phase, and the substance when heated transfers solid to vapor by absorbing the latent heat of sublimation from the surrounding. We can observe here, I repeat this sentence, at a pressure below this triple point line, the substance cannot exist in the liquid phase, and the substance when the heated transform directly from solid to vapor by absorbing the latent heat of sublimation from the surrounding. Okay, this PV diagram is for a pure substance other than the water. In earlier slides, we have seen the PV diagram for pure substance, which is water. For water we have seen, but this is the PV diagram for pure substance other than the water whose volume increases on melting. Okay, because when you consider water as a pure substance, there was a peculiar characteristic of water, but that is the reason why we will have different PV diagram for water. But for other substance other than the water, we have this PV diagram. Till now we have been discussing about a PV diagram for a pure substance. Now we will discuss about PT diagram for a pure substance, which means that pressure versus temperature diagram. If the phase changes are plotted on PT coordinates, the diagram is as shown in this figure. The diagram will be as shown in this figure. 1 to 2 here, solid heating. Okay, from 1 to 2 it will be solid heating, and from 2 to 3, okay, these three lines are carried out at different pressure lines. This is all these three are heating process carried out at different constant pressures. Okay, so 1 to 2 solid heating here, from 1 to 2 any line you can consider. 1 to 2 solid heating, and 2 to 3 melting of ice at 0 degree Celsius, and 3 to 4 liquid heating, and 4 to 5 is the vaporization of water at 100 degrees Celsius, and 5 to 6 heating in the vapor state. Clear? Now let us have different types of curve here. Fusion curve. The curve passing through the 2 and 3 points is called fusion curve. You can observe the curve passing points 2 and 3 is called fusion curve. Then vaporization curve, the curve passing through the points 4 and 5 called vaporization curve. You can observe here 4 and 5 vaporization curve. And similarly, sublimation curve, if the vapor pressure of a solid is measured at different temperatures and these are plotted, the sublimation curve will be obtained. Where it is sublimation curve? Okay, here you can get the sublimation curve. When you will get sublimation curve is, or how to get sublimation curve is, if the vapor pressure of a solid is measured at different temperatures and these are plotted, the sublimation curve will be obtained. Okay, the diagram what we are seeing in this slide is called HS diagram or Mollier diagram for pure substance. Okay, now we will discuss about what are the lines we will use in Mollier diagram to solve numericals on pure substance. So let us discuss one by one. A very important line we will use in the Mollier diagram is, or you can see in the Mollier diagram is, dry saturated line. Dry saturated line means the dryness fraction at this line or on this line is 1. You can observe here, it is the dry saturated line. This dry saturated line divides the Mollier chart or Mollier diagram into two equal parts, that is wet region and superheated region. Now dryness fraction lines. Okay, the dryness fraction lines are present only in wet region. You can observe in the Mollier diagram. If you open the Mollier diagram, you can observe these lines, these horizontal curved lines. We can observe the dryness fraction line present only in the wet region. Okay, in this region, this dryness fraction line will be present. In the Mollier diagram, we will also see constant temperature lines. You can observe in the Mollier diagram, the lines will be like this. These are all constant temperature lines. The constant temperature lines are present only in superheated region. You can observe in the Mollier diagram. Then constant or specific volume lines. The specific volume lines present in both wet and superheated region. If you observe Mollier diagram, these lines, these kind of lines we will get to see. So these kind of lines we will call it as specific volume lines. These specific volume lines present in both wet and superheated region. And in Mollier diagram, we will also see constant enthalpy lines and constant entropy lines. Okay, these in the Mollier diagram, these horizontal lines are nothing but constant enthalpy lines, and these vertical lines are nothing but constant entropy lines. Now we will discuss about one of the very important concept which is related to steam and its generation. And now we will try to draw steam generation curve of a steam and the terms involved in steam generation. Okay, by observing this figure you can define these following terms. Let us define sensible heat. Sensible heat is the amount of heat required to rise the temperature of 1 kg of water from 0 degrees Celsius to the saturation temperature Ts degree Celsius at a given constant pressure is defined as sensible heat or enthalpy of liquid. The symbol we will use to represent sensible heat is HF. In the diagram you can observe here, so from this point to this point, this heat we will call it as sensible heat HF. This heat is amount of heat which is required to rise the temperature of a 1 kg of water from 0 degrees Celsius to saturation point, up to saturation point. We will call it as sensible heat. So if you heat water under atmospheric pressure, then saturation temperature is 100 degrees Celsius. Now let us define latent heat. The symbol is HFG. Amount of heat required to evaporate 1 kg of liquid at saturation temperature Ts to 1 kg of dry steam at saturation temperature at a given constant pressure is called latent heat of evaporation or enthalpy of evaporation. From this point to this point, from B to C, the amount of heat required to convert 1 kg of this water into 1 kg of dry saturated steam. That amount of heat we will call it as latent heat or enthalpy of evaporation. Then amount of superheat. The amount of superheat is to, or which is the heat which is required to rise the temperature of dry steam from its saturation temperature to desired higher temperature at a given constant pressure is called amount of superheat or enthalpy of superheat H. From here to here it is enthalpy of or amount of superheat. Now saturation temperature, the temperature at which the liquid begins to boil at stated pressure is called saturation temperature. Saturation temperature is the temperature at which the liquid begins to boil is called it as saturated temperature. Now superheated temperature. Superheat temperature is the temperature of steam above the saturation temperature is called superheated temperature. Now we will discuss another important property which is related to steam or which decides the quality of steam is called dryness fraction of steam. If in 1 kg of liquid vapor mixture, x kg is the mass of vapor and 1 minus x kg is the mass of liquid, then x is known as the quality or dryness fraction of the liquid vapor mixture. Overall, the dryness fraction represents the how dry the steam will be. We know that if you want to call steam as a better quality steam, the moisture content will be very less, which means that dryness fraction will be more. Therefore, quality or dryness fraction indicates the mass fraction of vapor in a liquid vapor mixture. Okay, so this is the formula to calculate dryness fraction x. Okay, where in this formula mv and ml are the masses of vapor and liquid separately in a mixture. The value of x varies between 0 and 1. If the value of x is equal to 0, then it is saturated liquid, which means that completely liquid it is. If x equal to 1, then it is dry saturated steam. The quality of steam will be completely dry saturated steam. There is no moisture content in it. And if the value of x lies between 0 and 1, it will be wet steam. Okay, we will have different states of steam or 3 different types of steam: wet steam, dry saturated steam and superheated steam. Okay, for wet steam, so name itself will tell that for wet steam the x values lies between 0 and 1. So while dealing with the wet steam, we need to consider the dryness fraction x. So H equal to HF plus x into HFG. H is nothing but it is enthalpy here. If you want to calculate the enthalpy value of a wet steam, then enthalpy value of wet steam H is equal to sensible heat plus product of dryness fraction into enthalpy of evaporation. Similarly for entropy and similarly for specific volume of wet steam. This set of formulas will be used for wet steam. And when you talk about dry saturated steam, no need to consider this dryness fraction content, because here for dry saturated steam the x value is 1. So that's why for dry saturated steam Hg equal to, which means that enthalpy of dry saturated steam is equal to sensible heat plus enthalpy of evaporation or enthalpy of vaporization. Similarly for entropy, similarly for specific volume. And for superheated steam, if you want to calculate the superheated enthalpy or enthalpy of superheated steam, if you want to calculate, it will be sum of, it is the enthalpy of vaporization plus product of specific heat of particular liquid at constant pressure into this temperature of superheat or difference between the superheated temperature minus saturated temperature. Now we will discuss about measurement of steam quality by throttling calorimeter. Throttling calorimeter is a device which is used to measure the quality of steam or dryness fraction of a steam using throttling calorimeter. In the throttling calorimeter, a sample of wet steam of mass m and at a pressure P1 is taken from the steam main through a perforated sampling tube. Okay, from this steam main we will take sample of wet steam to measure its dryness fraction. Then it is throttled by partially opened valve. Then the steam which is absorbed, which is taken from steam main, will be sent to this partially opened throttle valve. In the throttle valve, what happens is it undergoes disturbance. When the steam undergoes disturbance, its temperature increases. Okay, then it is throttled by partially opened valve to a pressure P2, which can be measured by mercury manometer, which is provided over here, and at temperature T2, so that after throttling the steam is superheated condition. Because of the increase in the temperature, the steam undergoes increase in the temperature and the wet steam becomes superheated steam. Now the steady flow energy equation gives the enthalpy after throttling is equal to enthalpy before throttling. Okay, we should remember one thing: if you apply steady flow energy equation, enthalpy before throttling is equal to enthalpy after throttling, which is H1 before throttling is equal to S2 after throttling. So before throttling the steam is wet steam. So that's why how to calculate the enthalpy for wet steam is HF at pressure P1 plus into multiplied by dryness fraction x1 at 0.1, and it is enthalpy of vaporization, which is equal to H2, which is enthalpy after throttling. Enthalpy after throttling is superheated steam. There is no dry moisture content here. So from this equation, x1 dryness fraction of a steam of this steam main, which is there in the steam main, can be calculated using this formula. So this is how throttling calorimeter works.